Hein.
Parfait.
Okay.
C'est très bien. Voilà, c'est bon. Donc bonjour à tous. Merci d'être venus relativement nombreux pour l'instant. Donc pour participer à ce premier séminaire du laboratoire PIMM pour l'année 2021. Donc j'en profite pour vous souhaiter une bonne année à tous, notamment à ceux que je n'ai pas encore croisés. Donc pour commencer le séminaire cette année, on a la chance de recevoir aujourd'hui Laurence BODELOT, qui est chercheuse au laboratoire de mécanique des solides de l'école polytechnique, et voilà, qu'on a la chance de voir, et qui va nous parler. Du coup, je ne sais pas parce que je n'ai plus les diapos sous les yeux.
Ah, ça m'a travaillé. T'inquiète pas, je dirais.
Tu présenteras ton sujet, c'est parfait. Donc, je te remercie d'avoir accepté l'invitation et puis on va t'écouter avec attention.
Ok.
Merci à tous.
Merci, Justin. So hi everybody. Today I'm going to talk about coupled magnetomechanical behavior of magnetorological elastomer materials and structures. So this work has been conducted at Laboratoire de Mécanique des Solides. It's a joint effort with my colleague Costas Danas, who's a numerical person, and Nicola Triantafidis, who's more a theoretician, and myself, who's more on the side of experiment. So we have 3 students working on this: Tobias Possinger, Erato Psarin, and Jean-Pierre Voropaev, who all have defended so far. So first of all, what are magnetorheological elastomers, which we for short call MREs? It's first a composite material. So you have an elastomer matrix, a soft one, in which you come and disperse micron-sized iron particles, which gives you this mix here. Beyond that, this composite material has something more. It is an active material.
Excuse-moi,
ouais,
c'est juste pour être sûr que les gens voient bien tes diapos.
Alors ça, je peux pas
Est-ce
te
que
dire.
vous pouvez le confirmer?
Moi, j'ai le contrôle, tu m'as volé le contrôle.
Moi, je ne les vois pas. Moi, je les vois
voilà,
pas.
c'est pour ça. Donc, en fait, je vais prendre le contrôle.
Je les vois, moi.
Il faut cliquer sur les diapos, si je peux me permettre.
Oui, mais c'est pour l'enregistrement aussi.
Là, je peux bouger mes diapos, c'est bon. Mais par contre, je peux pas bouger ma souris.
Le problème n'est
pas...
pas...
Moi, je vois rien non plus. Hein.
Voilà, en fait, on voit ta caméra. Parce que tu es en... voilà, tu es en évidence. Donc, je vais arrêter de te mettre en évidence. Je vais mettre les diapos. Voilà. Et...
C'est bon?
Normalement, c'est bon, là. Est-ce que les gens peuvent confirmer qu'ils voient les diapos?
Oui, tout à fait, oui.
Bon, ça,
merci beaucoup.
Alors, le seul truc, c'est que
moi, je n'ai pas. Mais bon, pas.
Moi, je ne vois pas non plus. Hein.
Ouais, je vois pas.
Alors
là, ça, c'est pas moi. Hein, mais
mais non, mais il suffit d'aller cliquer dedans.
Oui.
Mais qui clique
On clique dedans, ça marche.
Dites-moi.
Nous.
Non, ceux qui écoutent, il faut cliquer dans la fenêtre.
Ah, voilà.
D'accord, oui. Ça y est, c'est bon.
Désolé pour
non, c'est pas grave. On va
cette interruption.
Ok, donc là, vous avez la diapo MRE, c'est ça?
Oui.
C'est bon. Par contre, tu vois ma souris?
Oui.
Bon, super, parce que quand je mets le pointeur laser, là, du coup, j'ai contrôle sur rien du tout. Bon, alors, donc, vous voulez que je reprenne, du coup?
Non.
Tu peux y aller.
Bon, j'aurai juste pas la souris, hein, tant pis, j'essaierai d'expliquer. So magnetological elastomers, MRE for short, it's a composite material. It's also an active material. In this active material, the matrix is completely transparent to the magnetic field. It does not interact with it. Only the particles will interact with the magnetic field and they will align themselves, as you can see with the little arrows that I drew. They want to align along the lines of the magnetic field. And in doing so, because we have a very soft matrix around, they will drag the matrix along with them. And so that will cause deformations that we call magnetostriction. It's a magnetical induced deformation. So with these kinds of materials, we have 2 different types of applications. First of all, if you tend to constrain the boundaries of your material and apply a magnetic field, you will see a change in stiffness. So that's why a lot of people propose to use them as tunable dampers. Now, if you do not constrain the boundaries, you will have strains, large strains and large displacement, which is interesting for interactive surfaces, which we also call haptic surfaces. So you can see here, bottom right, this surface where you can create bumps and dimples, maybe like a 3D iPad. So we're talking about applications, but we have no MRE-based devices at home. And the reason behind that is that predicting their behavior is not that easy in terms of modeling, especially because, as I showed, we have that cartoon where all the particles have small arrows. They realign along the lines of the magnetic field. But what's important too is that when a particle magnetizes itself, it creates a perturbation field around itself. So in which case, they perturbate the magnetic field of the neighboring particles, which means in terms of modeling, there is no way you can predict the behavior of this material while taking into account every single particle. So you have to take what we do, which are more phenomenological approaches to look at their behavior. So our main idea was to characterize their behavior. So we have a constitutive law, and so we can finally address the question of structural modeling, propose devices made with those magnetorological elastomers. So for that, we started from the beginning, sample fabrication, then material characterization under coupled magnetomechanical loading, so that we had enough data to obtain the parameters of a phenomenological model that I will show after. The only issue we encountered is that when we tried to identify those parameters, we realized that those materials were suffering from structural effects, which means you cannot identify their behavior just analytically. You will need to add a step where you identify everything via finite element. Another aspect that was a problem for us at the beginning was the fact that all these materials are extremely unstable. So we'll see throughout the experiments a lot of instabilities, but in the end, it turned out that if you manage to harness them properly, they're actually becoming very useful. And I'll show two applications that we have developed where we harness those instabilities. So I'll start with the sample fabrication. So the particles that we're using are carbonyl-iron powder. Those are spherical particles, and their average diameter is around 3.5 microns. The matrix here is a soft elastomer, so it's Shor 0020, so around 40 kilopascal for Young's modulus. It's a two-part silicon, which is RTV, which means room temperature vulcanization. So to fabricate them, we have to take our particles, pre-treat them, I'll talk about it right after, weigh the particles, the amount of matrix, mix all that together, then degas the mix and pour it inside the mold that we can put under temperature to accelerate the curing, even though it would cure under 24 hours under room temperature. So about the pre-treatment, when we were putting hard particles inside a really soft matrix, the first thing that we thought about is that we would have debonding, because, you know, hard particles inside a soft matrix. So what people do usually when they are putting hard particles inside a soft matrix is that they treat them with a silane primer. So it's just a chemical that helps you enhancing your bonds between your particles and your matrix. So that's what we did. So I have here some SEM pictures. So at the top left, you see normal particles. On the right, they are treated. So they have a coating of that silane primer. And then if we take two samples, one treated and one spray coated, cut them and pull on them inside a scanning electron microscope, we can see indeed the effect of the silane primer. On the left side, you see that the matrix detaches very cleanly from the particles. And then on the right side, you can see that thanks to this silane primer treatment, the matrix remains attached much better to the particles as you pull on your sample. So these pictures are nice, but it's still at the very microscopic scale. And so what we're going to do later is look at the macroscopic behavior of our sample. So we decided to see what was the effect of this silane primer on the macroscopic behavior. So here on the left, you have a classical tensile test, so nominal stress versus stretch, for a sample which is isotropic, I'll come on that right after, and which has a particle content of 210 PHR, PHR being the mass of particles per 100 grams of rubber. So here you have 210 grams of particles per 100 grams of rubber. And what you can see between the two curves, the orange one and the black one, is that they're exactly the same. So under purely mechanical testing, even up to 60%, there's no official debonding that we can identify. Now you take that same sample, put it under magnetic field and maintain the force to 0. So which means it's just deformation that's induced by the magnetic field. And you look at how much it deforms. You see that we have different responses when the particles are treated or non-treated. So we confirm that in another way, which is by plotting the Jacobian of the transformation. For the purely mechanical test, bottom left, you remain around 1, so you have an incompressible behavior. And then on the right, the sample which has been pre-treated keeps its J around 1, and the one that has not been pre-treated sees the J going up, which means you have a change of volume, and that is a sign of debonding between your particles and your matrix. And so to elucidate that, Costas did some simulations. So here you have a soft matrix and some particles inside, and then you're going to apply a large magnetic field. And you can see that locally, all those red dots here locally, you can have up to 200% strain locally around the particles, which explains why we see a significant debonding under magnetic field. In the mechanical tests, what happens is that those particles are entangled in the chains, and as you unfold the chains, they do not see locally large strains. So the conclusion for us was, in the end, we do not need to do a pre-treatment of the particles if we are doing just mechanical tests. But if we are planning on putting these samples under magnetic field, then we absolutely need to do a pre-treatment if we want to assume that our material is incompressible. Another thing about those samples and materials is the architecture. If we just mix the particles thoroughly and let the mix cure without any magnetic field, we obtain an isotropic sample. Now we can also decide to put the mix as it cures under magnetic field. And since the matrix is still viscous at the beginning, the particles will still have time to align along the lines of the magnetic field. And those chains or those columns will be locked in place as the material is cured. So that gives us transverse isotropic samples, and in our case, we created those chains or columns in the 3 principal directions of the sample. So you can see those alignments of chains here on those SEM images. Another and last point about the samples is the shape. So when we're doing mechanical testing, we want to have uniform quantities in the gauge area. So that's why we started with the first sample here on the left, which is a classical dog bone sample with a rectangular cross section. If we are simulating this sample under magnetic field, you may see in the middle that we have yellow and green, which means just it's not uniform in terms of magnetic field in the gauge area of the sample because of the corners. So with these samples, we cannot really envision doing material characterization. So that's why we went for the second type of sample initially, which are also dog bone shaped samples, but this time the cross-section is circular. And now it's better because you can see that in the gauge area, we finally have uniform magnetization. However, you can see large gradients in the heads, so those red, orange, and so on. And we were wondering how this may contribute to the response of the sample. So to elucidate that, we came up with a third geometry of samples. Here you have at the body of the sample is a nearly ellipsoidal body made of magnetological elastomer, and the heads are just 3D printed and two together are glued together. So now on the simulation on the right, you see indeed the only magnetic part is that ellipsoidal body, and it magnetizes fairly uniformly. So now we take those two last samples and put them under magnetic field. And what we do is that we maintain their displacement. So we see how much the sample exert, how much force they exert on the setup. So the solid line in red, it's the sample with the magnetic or magnetological elastomer heads. And you can see it develop much more force than the one that doesn't have magnetic heads. So which means here that the heads of the sample would contribute to the response of the sample if they were magnetic, and in which case you would not be doing material characterization. So if we want to do magnetomechanical characterization, we have to use this third sample. The only problem that we have is that because we have a soft body stuck to rigid plastic heads, we have debonding. So now if I take the same two sample and do tensile test, just purely mechanical tensile test, when I plot nominal stress versus stretch, I can see that at some point the two curves are going to separate, and that's the sign that we have debonding between the body of the sample and its head. So in which case we cannot use the sample with the ellipsoidal body to do mechanical characterization above a certain stretch threshold. So we solved this somehow by deciding to take a fully MRE dog bone shaped sample for mechanical test, and then for the couple test where magnetic field is on, we will use the other sample with the ellipsoidal magnetological elastomer body and the non-MRE heads. So that's all for the tricks about the sample. So now I'll switch to our setup for magnetomechanical characterization. So it revolves around a large electron magnet, which can produce a 0.8 Tesla uniform magnetic field in a fairly large gap, 82 millimeter. The reason for having such a large gap is twofold. First, we wanted space to put our molds and to proceed to curing under magnetic field. And the other point is to be able to insert a tensile setup inside that magnetic field. So you can see on the right. So another view at that setup is given here. You can see a simple tensile machine, basically with two load cells at the top and the bottom, and then piezo motors. That's the only detail where your motors cannot interact with the magnetic field. So the piezo technology was insensitive to the magnetic field. And so all this setup is inserted inside the magnetic field, and we look at it with a camera. So another view is here. You have also a mirror making a 45-degree angle next to the sample, so that when we look at our sample, we see the front of the sample, but also its side. And also we have hole probe. So I'll explain what we measure with all that. So mechanically, with the load cells, we get the force applied on the sample. With the camera, we are performing optical extensometry. So for the vertical displacement along E3, we are just following dots. And then for the other transverse displacement, so E2 and E1, we are performing border detection simply based on contrast differences. So that's all for the mechanical measurements. Now, for magnetics, it's a little more complicated. So when you have a magnetic field, a uniform magnetic field here in air, and then you put a sample in it, what happens equation-wise is that you see that you have M, which is the magnetization of your sample, and then H1, it's the perturbation field around your sample. So in practice, when we put our sample, we see that. So the pink circle is the sample, as we said, because its cross-section is circular, we have uniform magnetization inside that sample, but we can see all around that the field is perturbated and is no longer uniform. So in the end, to know how the sample responds to this magnetic field, we need to have two quantities to measure, H1 and M. So to do that, we are using the equations that are recalled here, which is curl of H equals 0 and divergence of B equals 0. So what it tells us basically is that at the back of the sample, where you have the box with hole probe 1, you have continuity of the tangential component of H. So that means that at this point, M vanishes. So if you put your probe here, what you're measuring is H. And since we know H0, because that's what we applied, that helps us finding H1. The second equation tells you that you have continuity of the normal component of B. So then if you put your hole probe right at the interface on the left, hole probe 2, you will measure the full B in the sample. And since we've identified H1 and then we know H, then that gives us access to M. And so it's interesting to have those quantities, because the curves that they are called MH curves are telling you about how your sample is magnetizing. So that's all for what we measure. So I'm going to show you now the results. So we started obviously just by purely mechanical tests. We see fairly classical results, which means that if you plot stress versus stretch for a pure matrix, it's obviously softer than when you put more and more particles in your composite material. So you see the stiffness, the stiffness increasing with the particle content. What we also have, because we have composite with particles inside, we have the Mullins effect, which means your first loading will look different from the other ones. It corresponds to the fact that your particles are going to break some bonds permanently with the matrix. But after a few cycles, you will stabilize into a hysteresis that's going to remain the same. And of course, the more particles you have, the larger is your hysteresis. Another effect that we could also notice was the effect of a particle chain orientation. So if you have isotropic distribution of particles inside your sample, that gives you the softest response. Then for the two samples in blue and green, which have a particle as chains but perpendicular to the loading direction, we have the same response, so it's normal. And then the stiffest sample in the end is the one for which the chains of particles are aligned with the direction of the loading, which also makes sense because that's what you do when you reinforce concrete, you put the bars in the direction of the loading. So that's for the mechanical behavior. Now I'll switch to the behavior of those materials under magnetic field. So I'm going to start by the transverse isotropic sample for which we have chains of particles. Those chains of particles are perpendicular to the magnetic field, and they're also here coming out of the screen. What we're going to do is maintain the force equals to 0 throughout the loading. So it's like your sample is levitating inside the magnetic field. So we do that, switch on the magnetic field, and immediately the sample is going to rotate. And the reason behind that is the compass effect. Your chains are your chains. They want to rotate to align themselves with the direction of the magnetic field, and that they bring them with them the whole sample, and it rotates. So it's a structural instability, and we cannot measure anything on those samples. Same problem that we had when the chains are again perpendicular to the magnetic field, but this time in the plane of our screen, the whole sample wants to turn to align itself with the magnetic field. But because here we have the heads of the sample attached at the top and bottom, that gives us this bending. So we observe again that we do not measure any magnetostriction, so no strains induced by the magnetic field, but instead large instabilities and samples that we cannot control. The two samples that were not completely out of control, if we can say, are the isotropic sample and the transverse isotropic, for which the chains are already in the direction of the magnetic field. So when we take these samples, and especially the isotropic one, now we switch on the magnetic field, and we're going to see an expansion in the direction of the magnetic field. So that's the magnetostriction that we were trying to measure. And you can see here on the right, on the mechanical response, the largest stretch or strain is along the direction of the magnetic field, lambda 1. We have more or less 11.7 or 12% strain induced by the magnetic field. And we have also compressive reaction along E2 and E3. For the curve at the bottom, it corresponds to the sample for which the chains are already aligned with the magnetic field. We measure really, really small strains here. And then, in fact, we think that if we are able to cure the sample within its mold, remove the mold and right away proceed to the test, we would not see any strains. So for us, it's just residual strains due to the fact that the sample is not exactly in the same position than the position in which it was cured. And essentially here what happens is that the particles are already in their optimal configuration with respect to the magnetic field, so they don't need to move anymore. So that's why we do not measure any sizable magnetostriction with these samples. Another point that was interesting with that, and we need to note, is that my sample is isotropic. Okay, I put the magnetic field horizontally, and I have large strains in that direction. But the other two directions, so E2 and E3, they should behave the same. But they don't here, as we can see, and that is due to the fact that these materials suffer from shape effect. So here our sample is elongated, so we don't have the same overall dimension in the other directions, so namely the vertical direction and the transverse direction in the plane, and so this affects the way things deform. So that's the shape effect I'll come back on later. Last point about our test is the magnetization curve. What we see here is that the sample for which the chains are aligned along the direction of the magnetic field, they magnetize very fast, so the slope is really high, and they stabilize pretty fast and steadily, so we have a saturation that's clearly marked. For the isotropic sample, magnetization is much slower, and that is due to the fact that your particles need to move to realign slowly themselves with the magnetic field. So they need time to attain their optimal configuration. And what we see also that's interesting is that we do not attain saturation. And in fact, if we were pushing more and more the magnetic field, we would end up with an instability, which means so far we had magnetostriction, but we're not at saturation for the sample. If we put more magnetic field, the whole sample will end up rotating with the compass effect to align itself with the magnetic field. So we had magnetostriction, but it is not a magnetostriction that will last for any applied magnetic field. What we did also was test different samples with different volume content of particles. So of course, the more particles you put, the more magnetization you get. And you can see here that the curves stop at given magnetic fields, because above these magnetic fields, if you keep applying, the whole sample will rotate in order to finally saturate. And another point with those materials, the more particles you put, the more magnetostriction you get, so the more strain induced by a magnetic field. However, as you keep increasing the amount of particles, you do not get a linear effect. So if I keep putting particles, I'm not going to get larger and larger magnetostriction. At some point, there's a competition between the fact that when you add more particles, sure, you become more susceptible, but at the same time, you stiffen your composite. And then at some point, there's an optimal value called optimal filling factor, after which putting more particles won't give you more magnetostriction. So that's it for all the experimental results. Now I'll switch to what we have done so far in terms of modeling. So the idea, as I said, is not to model the particles because it's too complicated to compute their perturbation field, and we have hundreds of thousands of particles inside a sample. So the idea is to go phenomenological by proposing a free energy, isotropic because our samples are isotropic, and it's coupled. So inside that free energy, we have mechanical invariants, I1 and I3, as well as a magnetic invariant called I5, and sorry for the typo, I put twice I5, but there are two of them, I5 and I6. And so the idea is to propose a free energy that describes the shape of our curves. This free energy is separated in a purely mechanical one, which means if you don't have magnetic field applied, the orange part goes to 0. And you have, for the mechanical behavior, a hyperelastic model from Lopez-Pañas, proposed by Oscar. Now, if you switch on the magnetic field, you have a free energy that's coupled in the sense that inside your equation, you have I3, so a mechanical invariant, as well as the magnetic invariant. So the whole game was to propose a shape for this function. I won't go deeper into it, but at the end of the day, we have classical mechanical parameters to find, which are the one from the Lopez-Pañas model, and 4 coupled magneto-mechanical invariants. So for identification, we simply take our results. So to identify the mechanical parameters, we use simply the stress stretch curve and identify that fairly simply, which is something classic for elastomers. Now for the magnetomechanical test, we identify the parameters on 2 curves. The one that gives you magnetostriction as a function of the applied field on the left, where you see already that you don't get perfect match as you're doing the identification. And we also get some parameters from the magnetization curve, again, not perfectly, even at the identification stage. Now, what's more problematic is when you identify those parameters and look at what is the response of your model for the transverse stretch ratios, you see that the model predicts the exact same response for the 2 directions that technically are the same in an isotropic sample, even though they are not the same when we measure them on our ellipsoidal sample. And so that we cannot do much about it because the model is isotropic, so it will always predict something identical in those 2 directions. So the only way, if you want to identify the parameters, is in the end to conduct this identification via finite element modeling. So you have to mesh your whole sample. When you're doing rheological elastomers, you also have to mesh all the air around your sample as well. So it's already something that costs a lot in terms of computation. And then you need to proceed to parameter identification via finite element, which is also extremely costly. Doesn't give you really nice results when you see. On the left, we identify with 1% error, 6% error on the magnetic curve. And finally, we do a little bit better when we are plotting now the 2 transverse directions that do not behave the same. On top of that, because we're trying to find multiple parameters at a time, there's nothing that tells us that we actually found the absolute minimum in the optimization or identification problem. So this is really not something that's easy and clean in terms of material parameter identification for these materials. In fact, for now, considering the experiments, we're proposing to identify the parameters. In the end, with these materials, as I said before, we didn't like the fact that we had instabilities, but it turns out that instabilities are actually way more interesting for those materials and make our life quite easier in terms of device and modeling and finite element. So I'll show you 2 applications that we have done so far. The first one is a haptic membrane. So haptic is the interaction between man and machine, so like surfaces that move. And we decided to do a device where the motion comes from instability. So here you have at the top of the device an MRE layer inside a plastic casing, and then it's deposited on top of a coil with an iron core. And as you switch on and off the magnetic field, you can see that deflection of the MRE layer on the video on the right. And so the idea is that layer wants to fully turn, but because it's attached all around, it will deflect and create those jumps that you can see. So what we did also with this setup is do digital image correlation, stereo correlation here, to be able to measure the deflection of the MRE layer depending on different conditions. So the first thing that we did was use our 3 types of structuration of particles, namely having the particles parallel to the field, perpendicular to the field, or simply isotropic. It turns out that here any structuration actually stiffens your material. So in the end, the material that works better for this kind of applications are the isotropic materials, which is even better for us because they are easier and faster to make. Another thing is that when we add a core, we are going to concentrate the field really next and close to the layer, and we manage to get vertical displacement or deflection around 2.4 millimeters at the surface of this layer. And what's interesting to note is the current that we have to input in this small device comes down to 2.5 amps, which now actually makes the possibility of proposing actual devices that are manageable in terms of power consumption more realistic. So that's what the experiments. There is also a lot of work that has been done on finite element on that side. So again, the big issue with these materials is that you have to mesh the air around it. So when you show the mesh, it's already something that's very expensive because you have the MRE layer, the iron core and the coil, as well as all the air really far away around your system. The only thing they gain is on the formulation of the free energy. So they're still doing phenomenological models, but here you still have your mechanical part, just in case you just do not model any magnetics at all. You have your magnetic free energy and the vacuum one, because we also want to do one energy for the whole finite element mesh. The only new thing and thing that's easier is that in your free energy, there's no mechanical invariant that shows up. So you have J here, but so you need to talk to Kostas to know a little more about it. Visibly, to make your life easier in finite elements, you will consider your material slightly incompressible, so you don't have some elements locking effect when you're doing the computation. But anyway, the thing is, it's way more easy to identify your parameters of your model. In fact, here on the curve that I showed, they identified the whole behavior on one curve, the blue one, which is just the experiment without the core, and we're able to predict the behavior of the layer with the core. So that's for this first device. The second device that we looked at is inspired from a very classical mechanical problem, which is the problem of stiff, thin films on a soft substrate. So you know that if you compress the substrate, you will end up with a wrinkling instability at the top of your film. Well, in fact, if you deposit a magnetological layer on top of a very soft substrate that is not magnetic, and you can apply a really large magnetic field, you will have also this wrinkling instability showing up. And so the idea that Kostas proposed for ERC was the following: was because we have two instabilities that are collaborative in some sense, they're the same, we're going to play with both of them so that we reduce either the amount of mechanical compression we need or the amount of magnetic field we need to trigger those instabilities. So you can see here on the graph, at the bottom, it's the compressive strain you would need to go from stable to unstable. And so the idea is that you can compress a little bit less, but then switch on the magnetic field to go inside the unstable region. So we did some experiments to prove that. So we have a simple casing that applies a finite compression on our system of substrate and MRE film, and then we apply the magnetic field. And you can see from the top, when you apply very little compression, you can see it on the left images, you do not see much compression initially on the sample. You have trouble triggering that instability with the magnetic field that's increasing when you go to the right. Now, after a certain level of pre-compression, so 0.85, 0.8, you can clearly see that pre-compression on the left images. And as you switch on the magnetic field, you see that wrinkling cleanly appearing as you increase the magnetic field. And then at some point, what we noticed also is that if we compress too much, we can already see a small instability on the sample even before applying the magnetic field. And then we go to more exotic profiles, which are post-instabilities or post-bifurcation, called period doubling or localization. So I'll come back on that after for those who know a little bit about these classical shapes. So what we did again here was to model via finite elements. So again, when you're doing that, it's a huge mess in terms of mesh. You can see here on the right, you have your substrate in yellow. The film is just that little tiny blue layer or purple layer at the top. So there's very little MRE in your mesh. Around it, you have already a structured mesh from the air, and then because you need even more, a larger domain with the air, we they ended up doing unstructured mesh. So you have a really large mesh for just a small sample. The only interest of bothering doing that is that we have access via the finite element to quantities that we cannot measure experimentally. So namely deformation inside the film and also all the magnetic quantities. And that was very useful to develop these finite element model here, because when, as I said before, when you compress too much, you have secondary instability. So you go from wrinkling, which is those waves, and if you keep doing it, you're gonna get period doubling and so on. And when you have period doubling just in mechanics, you will have self-contact between those two ridges. And we did not see that on our sample under magnetic field. So there was some kind of discrepancy between the shapes that we could see mechanically and the one that we were obtaining under magnetic field. And so here, the simulations helped us understand what was going on. In fact, even though those two sides should have touched themselves, because they are magnetized and the magnetization remains along the direction of the applied magnetic field, they were actually pushing themselves away. And so that's why we never saw self-contact as could have been observed before in purely mechanical tests. So that's the main result of that simulation. So to conclude, experimentally, we figured out fabrication. We did some sample shape design and proposed a setup with the idea of doing some material identification, material parameter identification. This can be done analytically if you're just looking at the mechanics, and not at all if you're trying to look at the magnetic parameters. You will have to go through 3D numerical simulations, which is not very easy and fast. And in the end, instabilities, which we thought was a big problem at the beginning, tend to be quite interesting when you can harness them properly. First of all, it makes your life easier in terms of formulation. It also has nice application in haptics, and also in terms of energy that you need to invest to obtain large displacement. Well, it's actually more interesting. You get larger displacement at a given magnetic field than you would get in terms of magnetostructure. So now what are we going to do on the subject in the next years? Well, we would like to revisit completely the problem of magnetomechanical characterization to make it simpler. So basically proposing samples that do not suffer from shape effect, or at least suffer from shape effect that can be dealt with analytically to facilitate the identification. Look at the question of optimum filling factor, because in the end our samples were so complicated that when the matrix was too viscous, we could not fill in the molds. And we're also going to look at hard magnetic fillers, so that is particles that retain magnetization once you switch off the magnetic field. So as I said, in terms of modeling, try to propose experiments mostly to be able to analytically identify the material parameters. And in terms of instabilities, I think we're going to keep playing with that. With magnetic substrates, for example, we've done some couple experiments before, and it actually leads to very interesting phenomena. And we would also like to look at heterogeneously patterned films. That is, if you have a concentration of particles that vary at the surface of your film, we expect to be able to create surface roughnesses that are a little more complex than those 2D profiles that I've shown you so far. So yeah, that's it, and I'll be happy to take your questions.
Merci beaucoup. Thank you very much. Merci pour cet exposé passionnant. Je propose d'ouvrir la séance de questions. Est-ce que quelqu'un veut poser une question? Vous pouvez vous manifester peut-être en appuyant en levant la main. Sinon, pendant que vous réfléchissez à vos questions, moi je vais en poser une peut-être. Concernant le... Alors, peut-être, je vais peut-être arrêter l'enregistrement. Voilà, hop. Comme ça,